Okay, welcome. This is a introduction to polar coordinates. Let's go ahead and walk you through. So polar coordinates often are just a magnitude in a direction, but generally, let's give you an example. So imagine I start out at the northeast corner of Adams Park, and I want to go down to In-N-Out Burger. Well, if I was a bird or if I could fly, I would just jump in the air and go straight there. But because I can't trespass on people's property, I would probably walk down the road and then turn and go down Main Street to In-N-Out, which is slightly longer. So when are they used? Well, generally they're used when we have a direction and a distance, but we don't have any obstructions, so we can go straight to where we want to go to. This happens usually when you're in the sea, so for ships or for airplanes, and sometimes when you're hiking, when like a trail says, 5 miles this direction. So let's generalize or formalize what they are. So for any point out there, they're going to have an angle that we form off of the positive x direction or east, and then they're going to have a magnitude, and that's a distance that we go out to get to the point we want to get to. Generally, they have a x value associated with them, an x value that we go kind of like the blocks that we go, in this case, -3, about 3 blocks west, and then we go up as well. In this case, it would be 4. And so like the Cartesian coordinate for this would be -3, 4. Whereas if we were in polar coordinates, it would have to do with our angle theta and our magnitude of 5. So let's just compare Cartesian and polar coordinates. Cartesian always has an x and a y value that a point is from the origin. So in this case, the point would be at 3, 4. Whereas in polar coordinates, it always has an angle theta off of the positive x and a magnitude r, or distance from the origin. So how would we even measure theta and r? Well, if we have our Cartesian coordinate, we can drop a vertical and drop a horizontal, which are going to be your x and y values with your Cartesian coordinate. For this triangle, we can solve for r using the Pythagorean theorem, finding that r is 5. Theta, or the angle, is always going to be a little bit more complicated, but we do have some useful values here in the right triangle. Using right triangle trig, we have the horizontal and vertical, or the opposite and adjacent to theta, and so we can use tangent, and then use tangent inverse to find that theta is tangent inverse of 4/3, or about 53.13 degrees. Now, generally, we don't always have a Cartesian coordinate, or we don't always have a polar coordinate associated with some point, and so we want to figure out how can we go from one to the other. So here, let's talk about going from Cartesian to polar coordinates. Well, if I have some Cartesian coordinate a and b, I know that the distance that point is from the y-axis is a, and from the x-axis, the distance is absolute value of b, or the y value. Now, if I want r, I can form the right triangle. First, notice that theta comes from the positive x, so it's not going to be the same as this angle b. Now, I can drop the horizontal, and we find that we have this right triangle with b. And then using the Pythagorean theorem again, we find that we can use the absolute value of a and absolute value of b, and then r for the Pythagorean theorem, giving us that r is the square root of a squared plus b squared. Now, if we want to solve for theta, it gets a little bit more complicated. Theta, of course, isn't in this right triangle. We can solve for b with right triangle trig. So we have to use the fact that theta is 180 degrees minus b. Now, to solve for b, once more, we just want to use tangent because we know what the opposite and adjacent are. In this case, the opposite will just be your y value, or magnitude of b, and adjacent will just be your magnitude of a. Now, b, of course, will just be tangent inverse of b over a, and so we can just go ahead and substitute that in for theta. A disclaimer is this value will be different for every quadrant you use because we have to always measure for that angle b, not for theta. Now, imagine if we're going from polar to Cartesian, then we'll have a distance r, and we'll have the angle theta. And then that distance r can be anywhere on this circle based on our angle theta. But recall, imagine if that radius was 1. For any angle theta, if we have a radius of 1, we end up forming the unit circle. And on the unit circle, our x value will always be cosine of theta, and our y value will always be sine of theta. So our Cartesian coordinate will just be cosine of theta, sine theta. Now imagine if we shrink down that unit circle and extend it by r, because we want a radius of r, or a magnitude of r, not a radius of 1. And so, because they're similar triangles, the values of the triangles are going to scale up the same way that the hypotenuse or the radius did. So the y value is going to become not sine theta, but now r sine theta. And the x value is going to become instead r cosine theta, giving us a x and y value pair, a Cartesian coordinate of r cosine theta, r sine theta. Now in summary, a polar coordinate is just a distance and a direction, that distance always being the straight line distance like the bird flies, and the direction always coming off of the positive x or east direction. Now if we want to go from polar to Cartesian, we just have to consider scaling off of the unit circle, and this gives us that our horizontal and our vertical values are just r cosine theta and r sine theta. In summary, for polar to Cartesian coordinates, if we have a Cartesian coordinate of AB, then we know that we have some right triangle in which we can measure the radius using Pythagorean theorem, always giving us square root of a squared plus b squared. And the angle theta, we can just use right triangle trig for. It always will depend on the coordinate you're in. Now, there are some extra things that can happen with polar coordinates, like we can have our angle theta, which can usually vary between 0 and 2 pi like our unit circle, but that angle can be defined on any value. And then furthermore, our radius in this lecture, we have assumed our introduction was positive, but we can always define it as negative, like the orange vector negative r. And these are some references that you can make use of. They have some extra information, but beyond that, this is an introduction to polar coordinates, and I hope it was useful.